events, sort of like the Olympics, you know, every 4 years, or like the World Cup, Soccer World Cup. And, but there are also some symposium in between. And the last conference was in Fortaleza, Brazil. And the next one, so there will be a symposium in San Jose, Costa Rica, 2021, not in 2 years. If you want to know, we can discuss that later. And then there will be the conference, the 14th conference in Montreal, Canada. So as you can see that over the years, this conference has been to Europe, to US, North America, South America, and Asia. So it's really covering, and maybe one day in Africa, who knows. So a bit of the mission, it's to encourage the research and technology exchanges in this field of bituminous materials and structures. So there are a number of things around this. And there is a network, and this network, we're trying to grow this network, but that includes connections across the world, as you can see, AAPT, so in the US, CTA in Canada, ITA in Europe, JRCA in Japan, MESAT in Middle East, NAPA in the US, RILEM, which is international, and SABITA in South Africa. So it's very international, and we're trying to increase this relationship. Just to update you about the board of directors. So our new chair is Galen, and I am now the past chair. It's kind of weird to become past, but I'm past, and as you can tell from my hair, I'm more and more from the past. And we have Louis as the vice chair. The one thing we have in common on those pictures, I think they are kind of not taken yesterday or the day before, so we look younger. That's nice. And we have Mike, who is the executive administrator. He's the one actually working. All the others are here for fun. And then there is a whole bunch of directors at large, and you know most of them, and they represent various countries in the world, and so we aren't going to go through all of them, of course. Okay, so. And then we also have association members, and we have Audrey, who is representing NAPA. I think I saw her in the back. Hi, Audrey. We have Syed Salman from Sabita and Koji Yokota from Japan. So, and then one of the important things of the ISAP, there are technical committees, 3 technical committees actually, and you can see what they are about and who are leading those various committees. And asphalt pavement environment might be the closest related to what we're going to be talking about today. Then there are a few events which are related somehow to ISAP, so because of the network that we discussed a little bit earlier, so AAPT, that's where we are at the moment. Hope you're going to have fun during those days at AAPT. And then there is a ITA conference this year. And I can't read that's in Granada, but I think that's in June. But we don't have the monitor, so. All right. And then there is this international symposium on asphalt pavement and environment. And there will be actually 2 events this year, one in Italy and another one in South Africa. So in September and October. And then there is a CTA in Montreal. So if you want to listen a little bit more French with a different accent, I recommend CTA in Montreal. That will be a lot of fun, I'm sure. And then 2020, just one, but that's an important one. We have the ISAP Day, as every year we organize an ISAP Day, the Sunday of TRB. So that would be January 12th next year. All right. There are a few benefits to be ISAP members. I just want to point out 3 of them. being an ISAP member gives access to the papers, which have been published in the various conferences. It gives also reduced fees for ISAP conferences. In fact, anytime you go to an ISAP conference, you get automatically the membership. So it's also a way to combine both. And then there is a free membership for students. So it's a good opportunity to join an international network. And that's all I want to say about this ISAP. And if we want to, we can discuss more during the reception about it later. So let's switch to the real reason why we are here today. And so to co-chair, there will be Kamilla. So Kamilla Vasconcelos, she's also coming from another part of the world. So it's a little bit south of Wyoming, different climate. By the way, we had minus 30 F with a wind chill this morning in Wyoming. So it's a little bit of global warming, right? So Kamilla, she graduated in civil engineering in 2002 from Federal University of Ceará. I don't know if that's the, oh, okay, Brazil. And she also spent 1 year of exchange at the Technische Universität Karlsruhe in Germany. So she speaks German, not like, no, okay, not as a first language, right? Portuguese, English, a little bit of French, I know. She finished her master's in transportation engineering from this university in Brazil in 2004, and then in 2009 she got a PhD in civil engineering at Texas A&M. So she has quite the international experience. In 2010, she did a postdoc at Polytechnic School of University of Sao Paulo, Brazil. And she's been professor since 2011 there. And she's chair of the technical group of performance test of asphalt binders of the Asphalt Commission of the Brazilian Institute for Oil, Gas, and Biofuel. And she also co-chairs the technical group degree of binder activation, that sounds familiar, of the technical committee RAP of RILEM. She's involved in different research related projects. And with this, I want to welcome Kamilla, please.
Good afternoon, everyone. It's very nice to be here this afternoon. I think we're going to have a very nice global forum. As Mike have mentioned, we are going to miss one of the presentations that were on the schedule, but we are going to have 4 very nice presentations. So to start, I'll ask the first speaker, Heather Della. Is it right? Dr. Heather Della is the Sustainable Pavement Engineer for the Federal Highway Administration, where she managed the FHWA Sustainable Pavements Program and Pavement Life Cycle Cost Analysis Program. Prior to joining FHWA, Heather was the Director of Sustainable Engineering for the National Asphalt Pavement Association, where she managed programs that assisted producers, contractors, and designers in improving the sustainability of pavement construction. In this role, she led an industry effort to develop an environmental product declarations program for asphalt mixtures. Please help me welcome Heather.
Oh wow, this light is really in your eyes. Okay, well, I'm excited to be here. It's been 2 years since I've last attended a AAPT event, and if anyone knows at FHWA, we limit how many people can attend this event, and there's quite a fight or a line of who gets to go. So it's quite an honor to be an invited speaker today. I would like to start, with this figure from NOAA, and I think it presents a good motivation of why resiliency or the impact that climate makes on our pavements is important to the U.S. DOT or FHWA in general. In the last year, in 2017, $16 billion were spent on natural disasters, rebuilding from natural disasters. Now, that included a wide range of natural disasters, from flooding to wildfires, and not all of them actually impacted our infrastructure or pavements, but there are a few that we are still working on at FHWA right now, and that is from the hurricanes in Puerto Rico. It's not earth-shattering that we all know that environment does impact our pavements. This is something that we've known for some time, and a recent study, data mining, the LTPP database found that 36% of the damages was attributed to environmental features. So when we design pavements, we do consider the environmental parameters. However, in the past, we've always assumed that this is a historical trend and it's been pretty constant. And in the future, we're finding that this trend may not be true. If the climate, let's sort of say, were to change drastically, and our assumption that these historical climate trends were not flat and consistent, considering the lifespan of the pavement, with higher temperatures, we may see some more rutting. With moisture changes, we may see issues with soil shrinkage and swelling. And then with increased participation, we may need a stronger base or foundation because we may lose some structural capacity for our pavements. So here's just a few issues that we could expect if our climate changed drastically. At FHWA, we do have a strong focus on resiliency, and when we define resiliency, we define it as the ability not only to anticipate and prepare for these events, but also to adapt. And how do we withstand or respond to any and recover rapidly from any type of destruction? These pictures here are pictures how infrastructure has been impacted by extreme weathers over the years. In this presentation, I'm just going to go briefly over FHWA's resiliency program and policies to give you an idea of what we have in our policies right now, identify some of the available resources that are out there for you all to use and share, as well as highlight some future ongoing projects specifically to pavements. So starting with our program and policies, FHWA, the Planning and Environmental and Realty Group is really who manages the resiliency program. But resiliency is well immersed in not only our strategic plan. The strategic plan at the DOT level says that we should increase the effectiveness of ensuring that our infrastructure is resilient enough to withstand extreme weather. But it also is in an FHWA order, and that order says that all of FHWA should incorporate resiliency into our program when we consider program funds, projects, and research. Not only that, the resiliency and the consideration of the future environmental impacts is also in our regulations. The most current regulation that has incorporated the future climate is the asset management regulation. And this regulation requires the transportation agencies to put forth a transportation asset management plan. In that plan, you must not only consider the risks and the risks that climate could pose, but also include that in your life cycle cost for the agency or for that plan and managing your assets. And pavement is one asset that you must look at. So when you consider the various risks, there could be an immense list of them, and some of them are just political changes, etc. But climate is also called out in the regulation that agencies should consider moving forward. As a result, the Office of Environment and Planning has developed a program to integrate resiliency into transportation projects. And they're looking at it from a holistic point of view. They not only want to look at it integrating resiliency into the planning, but also the project level, design level, as well as the operation and management. And so there's a lot of resources. There's a big team that works on this, on how this should be done. From the planning level, they're creating a guideline for agencies that are putting together plans to incorporate resiliency into their approach. They have found that it is important to identify and call out resiliency if you want success of incorporating resiliency into your program. They're also looking at asset management, specifically with the transportation asset management plans that all the states are required to submit. They are looking at case studies with asset management plans. There is one state that looked at specifically pavements, and that was Tennessee. So they're highlighting the best practices that they've gathered from these case studies of states incorporating resiliency into their plans moving forward. And then in addition, they have guidance on how emergency relief funds can be used for improving the resiliency of your infrastructure needs. All of these projects that I have mentioned are spread across the U.S. They have worked in various regions and have conducted various pilots. So I encourage you to check out the resources available on the website if you want to dive in deeper. But moving forward, I would like to highlight just some of the pavement resources specific to that could be specific to asphalt pavements. And these span from case studies to tools as well as guidance. The first set of resources were case studies that they have done and conducted across the United States. There were several case studies that they looked at, and they were looking at how do we incorporate resiliency into that project level or engineering design. There are two case studies that I'm going to highlight focused on pavement type issues. One that was done here in Texas and one that is in Maine. The main lessons learned in Maine, they did a vulnerability assessment of their assets in Maine and identified that the future climate in Maine would likely have shorter or warmer climate and shorter winters. And this is important in Maine because Maine had higher load premiums for trucks in the wintertime when they had that extra strength because of the frozen ground. With this, they found that they were actually very vulnerable with the changing temperature in Maine because this season was getting shorter and shorter to maybe they would have to get rid of this premium. And not only could that, if they didn't get rid of the premium, it could cause damage on their network, but it was also going to have a huge economic impact on the trucking industry there. So that is what they found out in the Maine study. With the Texas DOT study, it was actually a roadway that wasn't built yet. So this is a proposed project. It was State Highway 170, and they were looking at how can we potentially influence design and build something more resilient. So they took the future climate projections and put it into the design models to see if that would change anything. In the case of Texas, they found that precipitation would decrease, and that would have increased subgrade support. So that was a good thing that actually happened with the increased climate, or the change of the climate. And then they also found that the temperatures would also increase, and particularly for asphalt pavements, they found that you may want to use a polymer binder for this particular case that was a little bit more resistant or flexible for the higher temperatures. When looking at this from a network level, they were from a project level, they were pretty happy because we have technologies that could meet the needs of the future climate, and they're available. There's no learning curve. However, and the cost isn't that much more. However, at a network level, they did say that the cost could be significant for a DOT adapting these strategies network-wide. So what can a DOT or agency do? The first thing that we suggest is to monitor your trends. You know, we're lucky that most of the environmental changes seem to not really impact the pavements within the current lifespan, but we are moving to designing longer life pavements. And as we move forward with longer life pavements, that may no longer hold true. And in monitoring these trends, maybe if you start to identify that there's certain environmental distresses occurring not when you would have expect, we may need to look back at our assumption of assuming that these historical trends of climate are remaining constant. One way to evaluate your vulnerability is FHWA's Vulnerability Assessment and Adaptation Framework. It's not just a framework of step-by-step procedures, but it does highlight various tools and resources along the way as you evaluate your network as well. And some of these tools I will highlight further on in this presentation. The Vulnerability Network Assessment, oops. I guess you can't, okay, here we go. Vulnerability assessment studies have been conducted across the United States, mostly done by the environmental group. And there, as I mentioned, the main DOT case study followed this assessment to identify that they were going to have impacts to their pavements, and especially with the trucking premiums. Within this tool, this assessment, one of the tools that it highlights is the CMIP Climate Data Processing Tool. And this tool just basically data mines from the U.S. Bureau of Reclamation climate data and synthesize it to the local climate data that you could expect for pavement designs. It takes two parameters that can get the projected temperature as well as the precipitation for your local area, and those future predictions is what you could expect. In addition, another tool that the Vulnerability Assessment Framework mentions is the Vulnerability Assessment Scoring Tool. And this tool just goes through and is an indicator-based vulnerability assessment to provide you to prioritize your potential vulnerabilities based on your various assets. So it lets you organize it in a way of what is the most vulnerable area and what is a little bit stronger you don't have to worry so much about. If you were to determine that your pavements are vulnerable to the future conditions, you need to look at different solutions. And FHWA has another tool that helps DOTs with this, and this tool is called the Adaptation Decision-Making Assessment Process. This is a risk-based approach, and it looks at the life cycle cost. It looks at maybe your political regulatory constraints, as well as resilience, and lets you look through all of these to figure out which approach would be best for the solution moving forward. In summary of all of these resources, there is a public roads article that was co-written between the Office of Infrastructure Pavements Group as well as FHWA's environmental group, and that's in the public roads on this topic. It's called Boosting Pavement Resilience, the same as the title of this presentation, that I encourage you to go read, and it will go into some of the details as well as provide the links to the resources I mentioned, as well as the Sustainable Pavements Sustainable Pavements Program has a tech brief specifically on climate change impacts to pavements. So those are two resources that you can reference. The Sustainable Pavements Program tech brief does have that table that mentioned out the key indicators that you could monitor for, as far as if you want to find out what trends could be leading to maybe looking at your climate data that you're putting into your models and designs. Moving forward, the Sustainable Pavements Program looked back at where we are now and what gaps do we have, and identified that there is a need for tools that can help us incorporate more sustainable practices in designing. And one of these practices is designing more resilient structures. So we are creating a guidebook that looks at how can we design more resilient pavements specifically for both asphalt and concrete pavements. In all of the work through the Sustainable Pavements Program, we do it with collaboration and stakeholders. So there's going to be a stakeholder group leading this effort in providing guidance on what type of issues DOTs are facing, as well as receiving some technical feedback through our Sustainable Pavements Technical Working Group. This project started this year, and we're currently identifying what are the gaps and needs. And we are expecting that this guidebook would be released in 2021. Another optional phase of this project is to do a workshop very similar to this, I would suppose, in where we bring together, climate scientists and the engineers and truly understand, share information on how climate does impact pavements and what can we do in our designs moving forward. Along with that conference, there is a conference that the Office of Environment is supporting through TRB on resiliency, and that is going to be held in 2019 in Washington, D.C. It may be more planning focused since that's who's sponsoring it, but I encourage you to check it out. And with that, if it goes, I'd like to summarize with how you guys can help in this effort. First, I think there needs to be a lot done in encouraging states to start considering resiliency and awareness that it is important to be looking at moving forward. The second is there are a lot of resources within FHWA. They're not out from the Office of Infrastructure, which I think many people are traditionally used to working with, for the pavements group that is. But we're working closely with the Office of Environment in this area and the planning group on how resiliency can be incorporated into pavement design, specifically in project decisions. And then always continue research. I think there's a lot more research that is needed in this area. And so anything we can do to growing the base of the knowledge base is important moving forward. With that, it doesn't want to go. There's my contact information if there are any questions. I think we're leaving questions to the end, though. Thank you very much.
Thank you, Heather. We're going to leave all the questions to the end, so we will invite all the speakers to the front, so you might ask to any one of them, okay? Let's move forward to the second speaker. The second speaker is Melissa Lyons from Australian Road Research Board. Melissa has been at ARRB for 7 years and has been immersed in applied research and consultancy projects in the bitumen, asphalt, and pavement materials space. Her current work sees her tackling projects on topics such as the use of recycled materials, such as crumb rubber and plastics in road infrastructure. Melissa has recently returned to ARRB after a 14-month secondment to Vic Roads as a pavement technology engineer and road delivery engineer. Please welcome.
Hi everyone. So my name's Melissa Lyons and I'm from ARRB, the Australian Road Research Board. So I'm a senior engineer there as part of the Sustainability and Resilience team. And at the moment, as Kamilla said, my work focuses on recycled materials in road infrastructure. So I'm keen to hear some of the presentations we've got coming up over the next few days. Our Sustainability and Resilience team is quite a recently new formed team. We're only about 6 months old. So we've got a lot of room to grow our capability, and we appreciate being involved in events like this. So I firstly want to thank AAPT and ISAP for having ARB here today presenting, and also to Kamilla and JP for chairing, and my fellow presenters. But also want to thank all of you guys for coming and taking the time out to listen to my presentation on resilient pavements in Australia. So I'm going to start off by just giving you a quick introduction to ARB, and then I'll set the scene by giving you some statistics on our climate and network and how that affects our pavement infrastructure. I'll also go into a bit about the research we do at ARB and how we try to be resilient, and also I'll do a quick case study on some findings on roads in Queensland. So the Australian Road Research Board, we're primarily a research organisation. We do some consultancy work. We try not to just sit behind our desks, but get out there and disseminate our knowledge through presentations like this, workshops. We create manuals, we do webinar programs. We also do demonstration and pilot trials as well. We work in the urban and rural space with all things got to do with road transport, so sustainability and resilience, structures, network design, autonomous vehicles, asset management, safety, all the important topics. And we also have a range of data collection vehicles that go out onto the roads every day. We also have our integrated system vehicles such as the iPave and ISAP, which are the pavement and surface collection vehicles. So we've actually got offices all over, hang on. We've actually got offices all around Australia. I'm from Melbourne, which is our head office, and we've just recently moved into a new research facility called, and we're being dubbed the National Transport Research Centre. Here we have a world-class laboratories looking at everything materials research, so it really gets down to the crux of it there. So we test all the road materials from pavement, asphalt and bitumen space. In Melbourne, we also have the accelerated loading facility, which there'll be some pictures later on of some testing that we do there. And yes, at the moment, we're actually got some foam bitumen stabilisation testing happening there. So, our road network in Australia. So, just to put things into perspective, I would like to start by placing our two countries on the map. So I think you can see the outline of North America in the back there. Australia itself is actually one of the smallest, well, is the smallest, flattest, and I think next to Antarctica, the driest continent on Earth. So our area is about 90% of that of the USA, covering about 7,700 kilometres square. And our population density is a lot smaller. So we've only got about 25 million people, whereas in America, 325 million. So we're a lot more spread out. We like the southeast side, and you'll see why when I show up the climate variations. But if you look in the top half of Australia, so if we draw like a semicircle across the top there, only 5% of our population live in that area, whereas the rest live, the other 95% live in the southern half, with 85% of people living in just our urban areas, so our major cities. Yep. Cool. So our road network, as you can see, it almost it's a mirror image of our population density. We have about 800,000 kilometres of road, whereas in America there's nearly 6 or 7 times that, with nearly 6.5 million kilometres. So in Australia we actually have one of the lowest network densities in the world. We have 10.6 kilometres road length per 100 square kilometres, so that's on par with Canada. And just as a comparison, the US has 66.4 kilometres per 100 square kilometres, so yeah, again about 6 to 7 times the amount of Australia. Australia's constitution is similar to that of the USA in that we're defined by the powers of the Commonwealth, but leaves the residual powers to the state. So all our states have individual road authorities. So Australian climate. So our climate is very fast and different over the country. Australia extends from 10 degrees to 40 degrees south of the equator. So we're given a wide range of climatic conditions from the full tropics up north, you can see in the green area at the top, all the way through the centre of and Western Australia, which is desert and grassland. And then if you move towards the south and the southeast, where most of our population is, we've got quite temperate conditions, although at the moment I'm not so sure. I've just come from Victoria, where we're battling about 30 bushfires at once, so wouldn't say it's that temperate. But the current climate challenges that we're facing on our roads include just the temperature changes. So in 2018, the Bureau of Meteorology reported that this was our 3rd hottest year on record in the past 10 years, and they're only projected to get hotter and with extremely fewer cooler days. We've also got variations in rainfall, which is one of the biggest influences on our country. We're seeing a trend towards wetter, longer wet seasons, and especially across northern Australia, while in central and south Australia we're seeing a lot more of the dry, high fire risk days and of course drought. With the increased rainfall, of course, in the north, we're getting the flooding. And so it's easy to say that this is the most expensive hazard that we face in terms of building resilient roads. The climate change scenarios predict that floods are only going to get more intense and more frequent over the years. So it's definitely a key area for us in improving our adaptive capacity. Just from a pavements perspective, we also have salinity impacting on our pavements in some areas of Australia. So we've got, this leads to higher water tables and subsequent reduction in structural strength with the salt, and also deterioration of the pavement as that salt holds the water. But it's important to note that we do have a vast climate, but we experience all of this in one day. So these photos that I've got up here are actually, were all taken on the same day. So we've got some bushfires, you can see in the background of the first photo there, which was in southeast of New South Wales. Then you go into the centre, we've got Queensland who are experiencing the floods. And then we go all the way to the south in Tasmania, where they just got snow only a few weeks ago, while at the same time battling bushfires only a few hundred kilometres away. So quite a vast difference there. But we're in fact a case study itself for other countries to consider in terms of climate analoguing. For example, countries with similar hazards are interested in what we do and what we're doing as a country in terms of adapting to these impacts. But to be honest, I think we've still got a lot to learn from international sources as well. So the road pavement structure in Australia. So here I've got a picture of a road that was destroyed by Cyclone Debbie about just under 2 years ago. So here the locals are stuck on a mountain after the landslides took out the road. So besides this being a bit of a dramatic picture, it also a pretty good picture showing the cross-section of our roads. So the typical pavements you're going to see in Australia connecting our major cities are those with a granular base, unbound granular base, and then a thin bituminous seal on top. So the extreme challenges that we face affecting a nation are the ones that occur at the same time. We've also got a low network density with large travel distances from our mines, farms, ports and cities. We've also got that densely populated urban areas, as I discussed, and on top of that we've got heavy loads with low traffic volume. So I think from a slide before I forgot to mention that only that 90% of our transport only occurs on 20% of our network. So although we don't have high volumes of traffic, we do have heavy volumes in certain areas. And of course we predominantly then have our light pavements as well. So the impacts of extreme weather. So here's just a simple flowchart showing the effects of extreme weather, starting from your immediate impacts all the way through to how it can affect in terms of economic-wide loss. So the impact of high temperatures is more prevalent in our bituminous materials, so our asphalt and our sprayed seals, whereas the effect of high rainfall is more prevalent in our pavement unbound granular structure. So given that the majority of roads in Australia are sealed road network and comprise of unbound granular pavements with the sprayed seal or asphalt on top, the importance of adequately considering the more frequent extreme weather events is becoming more and more important, and we definitely need getting more experience at it as well. So just some more pictures of what we experience on in some of our roads. So the first picture there, you can see we've just got the pavement structure has completely failed due to flooding, causing the surface to wash away. Then on the post to the other side, we've got we've got some bitumen bleeding, flashing. It looks like. So it's not uncommon for roads to reach at about 60 degrees Celsius on the surface, which I think is about 140 degrees Fahrenheit in Australia in very hot conditions. So, you know, we're significantly compromising the ability of bitumen to perform with these weather conditions. So So just a couple more photos. So the ones on the left, the left are show some landslides in Queensland. So the reason I had these photos is not necessarily to show you pavement failure, but we know that we've also got to think about the effect of the landslides falling on our roads. How we're going to clean it up. Is it going to affect the surface property, skid resistance if we don't clear these things from a safety point of view, and also having these materials there from a drainage point of view if the road keeps flooding. The picture on the right also may be a little bit dramatic, but it looks like, from the reason I wanted to show this picture, that it actually looks like the road, they have thought about the flooding, and they've wanting to build this road a little bit elevated. You can kind of see in the background there from the shoulder, it's got quite a big gradient there, but obviously the water's got through to the shoulder, and it's caused the pavement to fail. So these photos show the immediate impacts that happen on network, but obviously we've got that flow on that happens affecting nationwide. So just as an example, we've got some loss of connectivity. So here we can see the flow on effect from the extreme weather. Here we have the shortest route to get from two of our major cities, from Perth to Adelaide. So the one on the left shows the direct route is actually a 26 hour drive. And then when you move, if that road gets washed out by a flood, which is very plausible, there's only one way around, and that then triples your travel time and distance all the way, and you're actually probably going to hit more floods as you go up north. So from that perspective, our network density probably shows the vulnerability of our network density for there. Furthermore, in the Northern Territory, which is the centre north, I'm going to go back, is the centre north state there. We actually have annual road closures, so after the wet season, just because our roads can't keep up with the loads after them. So this obviously, leads to economic loss and things like that as well. So how do we be more resilient, and how do we better cope with our extreme weather events? So as Heather discussed and gave a really good introduction, we've got to take this holistic approach to things. So we've got your planning and design. You want to consider our material selection, make sure we're using fit-for-purpose materials more and more. We've got material specifications. Just from a local's perspective, we're slowly making a move towards more performance-based specifications. And then there's also the next generation materials, monitoring and modelling, and a lot of life cycle analysis, which we've just heard about, which I won't be going through today. So to help with this certain initiatives we have and to build professional capability and of course savings from in our road expenditures, we have initiatives such as the NACO program, which is the National Asset Centre of Excellence, and this is a collaboration between AARB and one of our state road authority in Queensland. And this program strategically targets road infrastructure related research through a multi-year committed resource program, and I'll be showing some of the results from some of those projects today. So just as a quick example of one of those projects, here we've got some research done by ARB under the NACO program that coordinated route-based upgrades such as the ones you can see in this picture here. So the Bruce Highway is one of the critical links along our east coast, but it's regularly cut off by floodwater. So in 2015, the Yeppoon floodplain was upgraded to be elevated about 3.5 millimetres on one side, creating a contraflow together, so 3.5 metres higher than the old road. And as you can see here, it has, I think this road was taken in 2017. You can see it's performed really well. So when the flood happens, the elevated road is able to act as a two-way road and still keep that connectivity there. So we've also got things like, in terms of planning and design, we've got the climate adaptation frameworks, which we use to help us with extreme events. So I suppose following on from what Heather said, we're strong believers in using international finders and adaptations. So we're currently undertaking research into how the PARC framework here, along with some other frameworks that's used on a more local base, can be adapted to Australia-specific climate risks. So this guide here was developed for authorities to identify relevant assets, climate variables, prioritising risks, developing robust adaptation responses, and integrating the findings into our decision-making process. So the framework also provides that life cycle interactive approach to climate change and adaptation, which is very important in terms of that whole life process. So now looking into some of the research we do at ARB. So here I have an example of some granular materials that are commonly used throughout our pavements in Australia, and they are quite often moisture sensitive materials. So you can see from the diagram, from the graph, that these materials are a function of the moisture content at the time of loading. We're seeing an increase in deformation with the increased moisture content, so we can tell when we need to intervene with our resilient pavement structures. This graph was generated using our extra large wheel tracker, which is in our laboratory in Victoria. This method was also compared and assessed against a full-scale ALF testing and showed some fairly good correlations. The reason we do these moisture tests is that moisture-related pavement failures is obviously one of the most common failures that we see in Australia, especially in northern Australia with the flooding, and therefore it's really expensive to repair. So as an example, I think Heather said that $16 billion was spent repairing your roads last year. We just had $6.4 billion just on one state of Australia repairing our roads in 2015 with 50% of these costs just going to the pavement. So you've got to, so that was, Heather had the whole country. We just had one state using, $6 billion. Okay. So moving more into the selection and design space, in an urban and semi-urban environment, we know that asphalt and bituminous materials can deliver good resistance to water and recover well from flooding, especially, but only if they're properly designed and constructed. So especially the use of materials such as those with polymer-modified binders, we can also reduce the risk associated with increased pavement temperatures. One example of material selection which gives us resilience in roads and also a lower cost to our community is the use of EME2. I'm not even going to try pronouncing that in French, but as you guys probably already know, this material gives us increased structural capacity and a high resistance to rutting in warm climates, and can also be built in thinner layers, therefore giving us our cost savings. We can also use, you can also see in the bottom picture there, crumb rubber modified binders, which are becoming more and more prevalent in Australia. They're already quite established in the sprayed seal area, especially in our southern states, but we've definitely got quite a bit of a way to go in terms of the asphalt space. Right now we're trying to work on opening up our specifications to allow for more crumb rubber and allow our industry to really give them the opportunity to show their technology in the area, and that's something we're working with our state road authorities on developing specifications there. The last picture on the top right is actually foam bitumen stabilised pavements being constructed at our accelerated loading facility. So I'm going to go focus a bit more on FBS. So as I showed you before, we have the typical Australian pavement structure, which is your granular base with your thin bituminous seal. But in comparison to what we can do in terms of building a more resilient road is obviously we can create this stabilised bases using in situ stabilisation. And although I'll be focusing on foam bitumen stabilisation, it's important to note we don't just look at that, and our NACO program actually looks at doing cement stabilisation, lime stabilisation, and also looking at recycled additives like fly ash. So, part of the ARB and Austroads, which is a research program that we've got in Australia, we've got research currently getting underway in developing significant improvements to the laboratory-based mechanic design methods being used for cost-effective materials, such as foam bitumen stabilisation. So using the accelerated loading facility, we're testing full-scale FBS pavements and recycled materials. The first phase of our testing program, from the picture you can see here, actually confirmed good rut resistance in warm conditions, and we've got a second phase currently being undertaken, which is assessing the resistance of fatigue cracking. So in the first phase, you can see the picture here, we've got our accelerated loading facility, which we built an FBS pavement with a seal-sprayed seal on top, or chip sealed on top, and then we subjected it to direct heating using heaters, which penetrated about 75 millimetres deep, about 40 degrees Celsius. I'm not sure how much that is in Fahrenheit. I think that's probably just over 100 degrees Fahrenheit. So warm climate conditions, and then we subjected it obviously to the repeated loading. And you can see from the graph below that our FBS, which does contain 50% recycled materials, so keeping up the sustainability approach as well, actually performed quite well in comparison to the asphalt. So there are many benefits of foam bitumen stabilisation, making them the resilient pavement of choice, or increasingly resilient pavement of choice in Australia. We've got the increased load-bearing capacity at high temperatures, the fatigue resistance, which we are seeing from our current studies, but they are also moisture resistant and can give us longer working times during our construction. So as I've mentioned already, we've had quite a few major flooding events in the northern state of Queensland, and in 2010 these photos actually were from a flood. They started to rebuild this road, and as they were rebuilding it, it actually flooded. So the picture up there is actually of the floods as it was being constructed. And so this was actually being built with foam bitumen stabilised pavements. And so you can see in the picture underneath how well the foam bitumen has actually held up compared to the shoulder, which was a granular material. It's completely washed away. So in terms of being time saving and money saving, it helped us from the get-go there. And from what I understand, they were able to, after obviously just a little bit of drying time and reconstruction of the shoulder, they were able to continue with the construction there. And I think we can agree that if it was an unbound granular material there, that road wouldn't be there after the flooding, especially during construction. So I'm just going to go through a case study now from Queensland. I'll go through. So following the 2010 to 13 floods in Queensland, there was a transport network reconstruction program undertaken to help repair the road network. ARB, as part of the NACO program, undertook a work looking at the application of the pavement technologies and treatment options that were used as part of this program. So as I showed in one of my previous pictures, we had Cyclone Debbie, and this hit Queensland about 2 years ago, and it caused major flooding across the eastern part of Queensland. And this is where our construction program is being completed. So you can see the path there, the red line of where Cyclone Debbie hit, and it caused everything from cyclone damage to flooding. So we had both slow onset and rapid flooding occurring as you move down the state. So there were sites along the cyclone path, which I can't disclose with you today, but there will be a report hopefully published soon that will show those specifically for those that are interested. But we had 9 sites that were looked at as part of the before and after of Cyclone Debbie that were foam bitumen stabilised, or even just plain bitumen stabilised. From this graph, this table, you can see we've got the before the stabilisation, which is the blue and black in some cases, and then we've got after the cyclone is the red. So In general, we can see no immediate performance impact from the cyclone. However, it's important to know that this surface condition data was collected not long after Cyclone Debbie hit, so we've still got a bit of monitoring and long-term pavement impact to look at there. So just going through each one briefly, we've got the first one which shows the rutting, I'm pretty sure. We can see that the rutting has, I'm pretty sure that there's been some maintenance in between these in 2016. So we're seeing a slight increase in rutting for the bitumen treated bases, but for the ones that were foam stabilised, we have seen a decrease. But as I said, I think there's been some maintenance there on the surface. In terms of cracking, we haven't seen really much change in that at all since the cyclone, except for the first road site there, which actually had an increase in cracking after the stabilisation. So obviously the treatment didn't help in that respect, and then for what's actually happened in the cyclone, I think that's actually accelerated your rutting and your roughness a little bit as well. So the roughness, again, that stayed pretty stable after the cyclone, but what I found interesting is the deformation compared to before the cyclone and after the cyclone. You haven't seen much change at all, which is really positive results. So, as I said, overall, we didn't see any significant immediate impacts. We've still got some monitoring to do, and it'll be an interesting case to keep watching. But out of the 55 kilometres treated, we're proud to say that only 4% of these were classified as non-performing, so having a poor performance or poor condition from the surface. 43% are still in the monitoring stage, so maybe just slight showing they've been classified as fair, so probably having some initial signs of deterioration there. But over half of them were seen as really performing quite well still. So just to end, I wanted to show another few photos showing what actually happened with some foam bitumen stabilisation constructed roads through Cyclone Debbie. So on the first picture there, we've got an intersection completely inundated with floodwaters. And just a few days later, we've then can see not only that we've got our road, the waters have subsided and our road has survived, but it's also open to traffic, which is something that we're really quite impressed with. So I think we've got some really positive examples of what's happening in Australia, and we've got a lot to learn still in terms of resilience. So any recommendations or comments are welcome. So thank you.
Thank you, Melissa. With that, we are going for the third presentation. For the third presentation, we are going to have Katie Haslett. Is that right? Okay. Katie is currently a graduate student at the University of New Hampshire, pursuing her master's degree in civil engineering under the supervision of Dr. Joe Sayas and Dr. Eshandev. She recently graduated from UNH in the spring of 2018 with her bachelor's degree in civil engineering. During her undergraduate studies, Katie was actively involved on campus as a student athlete on the women's D1 hockey team. She was a member of the Asphalt Material Research Group for 3 years, the UNH Honors Program, the Student Athlete Advising Committee, the American Society of Civil Engineering, and as a student leader with Athletes InterVarsity Christian Fellowship. She also served as vice president of the New Hampshire chapter of Tau Beta Pi. Now, during her graduate studies, she is focusing on a research project aimed at the development of best practices for rehabilitation of concrete with hot mix asphalt overlays related to density and reflective cracking. On the panel section at the end, we're going to have also Dr. Eshandev with us. Eshandev obtained his master's and PhD degree from University of Illinois at Urbana-Champaign in civil engineering in 2003 and 2009, respectively. At present, he is Associate Professor in the Department of Civil and Environmental Engineering at the University of New Hampshire. Jean's research interests include performance evaluation of pavements and paving materials, development and implementation of performance-based specifications, resilient design of transportation infrastructure, climate variability, impacts on infrastructure longevity, life cycle assessment, and cold regions pavement operability and performance. He is actively involved in the AAPT, ASTM, ISAP, RILEM, and TRB. One important thing to mention is that Katie, she was also this year AAPT Scholarship Award winner. Please welcome.
Good afternoon. Thank you, Kamilla, for the introduction. I'm really excited to have the opportunity to speak to you today during the ISAP Global Forum. The title of the study I'll be presenting today is The Impacts of Climate Change on Asphalt Pavement Maintenance and Rehabilitation Using a Life Cycle Assessment. And I'd like to acknowledge my advisors for this work, Dr. Dawei and Dr. Mo from UNH. So to start with just a brief outline of my presentation today, I'll begin with a short introduction to the study objectives and our motivation for doing this project, followed by some background information on life cycle assessment. I'll then jump into the methodology, really focusing on the incorporation of future climate data, realistic traffic data, as well as looking at the various maintenance and rehabilitation strategies. And then I'll go through some of our key LCA results and then finish with some conclusions. So one of the first major motivators for doing this study was that traditionally pavement design is focused on performance and economic factors. So we wanted to investigate the use of a life cycle assessment approach in the pavement design process. And typically when doing a pavement LCA, it's done using historical climate data. So we want to also look at the impacts of using future climate data, as we know that pavements are sensitive structure and their performance can be greatly influenced by climate. We want to take it then one step further and not only look at the effects of future climate during the operations phase of our LCA, but also look at the breakdown of user and operation costs from both an agency and user perspective with the inclusion of realistic traffic data. So with that, our first study objective was really first to perform an LCA on a section of interstate with the inclusion of real-time traffic data or realistic traffic conditions, the inclusion of future climate data, and then look at various maintenance and rehabilitation strategies over the service life of our roadway. Our second objective was then to quantify the increase in fuel consumption due to a decrease in ride quality, and we used IRI as our pavement condition index for this study, and that IRI deteriorates, as we know, with time during the service life of our roadway. And our overall outcomes from the LCA that we evaluated were global warming potential, cumulative energy demand, and life cycle costs. So just a brief background to make sure that we're on the same page in terms of some of the terminology that I'll be using throughout the presentation today. An LCA is simply just a technique that's used to evaluate both the environmental and the cost associated with a product over its design life through its various stages. So for a pavement, an LCA typically includes the excavation of your raw materials, the transportation then to your plant for production, the transportation once again to the site for construction, and then followed by your use, or as I'll refer to as your operations phase, which makes up a significant component of your LCA, and then followed by your end of life. And your end of life for a pavement can be somewhat challenging to define, because we know that asphalt is one of the most recycled materials in the US, and it's constantly being overlaid. So it can be challenging sometimes to draw that system boundary. And then just briefly, I'm sure most of us in the room are familiar with the International Roughness Index. It's typically reported in inches per mile or meters per kilometer. But the figure that's shown here is really to try to highlight an example of a performance curve where if we can try to optimize the timing of our maintenance strategies while the road is still in a relatively good or fair condition, we may end up saving more resources and money in the long run than if we allow our road to degrade to a poor or even failed state and have to reconstruct. So I'd like to start just with a general overview, and then I'll go into a little bit more detail on the methodology and how we incorporate future climate data as well as realistic traffic data into your LCA framework. So the first step, we needed to select a case study location. So we chose a 16-mile stretch of I-495 located just outside of Boston, Massachusetts, here in the US. And we assumed that our baseline conditions were that all vehicles travel at steady state during the service life or the operations phase of your LCA, and that there was no maintenance done or no treatment done during its service life. Our second step was to perform an inventory. So we needed to collect information on material properties, on climate data, as well as traffic volume counts, vehicle classifications, and also establish our pavement structure. The third step was really to incorporate the realistic traffic data. So there's a little bit more data mining that was involved with that, and we used a combination of Google Maps to generate our trip times and delays. And for those familiar with Google Maps, whenever you plan a trip, it gives you an estimation of the total duration it will take you to get to your destination from point A to point B, but it also gives you a nice color-coded map, and it goes from green, orange, red to dark red. And so using that, we can try to get an estimate on whether you're going to be traveling at, the appropriate speed limit, or if you're going to be sitting in traffic bumper to bumper in a dark red zone. The next step was to run Pavement ME to generate our pavement distress to develop our IRI curves. So we looked at a combination of 5 different cross sections and were able to generate those performance curves. And then our last step is to combine all of our results and really give an LCA impact assessment in terms of global warming potential, cumulative energy demand, and life cycle costs. So as Heather briefly touched on earlier today, climate downscaling is really just a name that's given to a process where you take information known at a large scale and you make predictions at a local scale. And so in this study, we utilized data from the CMIT-5 database, and the variables of interest were precipitation as well as the max and min daily temperature. And we were able to get that data from the range of 1950 to 2099. And as you can see, shown in the red box was our 12 by 12 kilometer grid where we collected projections using 21 climate models. Now, that data was on a daily basis, but for those familiar with Pavement ME, it requires hourly daily data in order to run your simulations. So there's a few more steps in this process, and the first one was really to take your daily max and min temperature and convert that into hourly increments, and that was done using a process that was developed by Valet et al. In 2017. And then we also needed to split the total precipitation into 24-hour increments for Pavement ME's input. And now's a good time to also mention some of the limitations and assumptions from using this data and also as part of this study. And the first is that this database only covers to the year 2099. And so when you're interested in performing an LCA that might extend beyond that time frame, you're now extrapolating from those projected models. And a second is that there's really limited IRI performance data that is out there on the effectiveness of different maintenance and rehabilitation treatments considering future climate data. So by that I mean, today we might know that by doing a microsurface, it might improve our IRI by 45 inches per mile. But is that also going to be true under future climate conditions? And so that's an area that certainly needs to be explored further to know whether that is held true or not. So shifting gears from the future climate data to the incorporation of the real-time traffic data, there's really two major components to your operations or your use phase of your LCA. You have your agency impact, and you also have your user impact. And so to start, we'll look a little bit at how we incorporate realistic traffic data into the framework. So we want to try to simulate realistic driving conditions, and to do that, we used a combination of Google Maps to generate those trip times, as well as to determine our congestion. And then we used Mass DOT's transportation data management system to collect information in terms of traffic counts, vehicle classifications, things of that nature. We then used that information in combination with EPA's MOVES, or Motor Vehicle Emission Simulator software, to generate our global warming potential and cumulative energy demand as a function of IRI. And so I'm not going to spend a ton of time walking you through, but the steps, we followed a 6-step process here on the left, where really we looked at determining your vehicle-specific power, and then using that to run through EPA MOVE software to get our global warming potential and our cumulative energy demand as our output, and then developed a function in terms of IRI that we could then apply to our different scenarios. So as I mentioned, the second major component to your operations phase is your agency impact. So what maintenance and what rehabilitation treatments are being applied during the service life of your road. And so for this study, we looked at a combination of microsurfacing, cold-in-place recycling, crack sealant, and mill and overlay. And in the study, we evaluated 5 different cross-sections. So shown on your right is a representative cross-section of what we simulated in Pavement ME, where we held the substructure and base layers constant, but what varied was that surface course, and it varied by material properties such as PG grade, air void, gradation, asphalt content, and so on. And so we used a combination of Pavement ME to generate our IRI, or our performance curves, as well as doing some literature review on the effectiveness of those different maintenance treatments during the service life to develop each set of curves. So the 6 different scenarios that we looked at, the first one was a do nothing and reconstruct, meaning that you build your road, you allow it to degrade to your terminal IRI, which we selected as 172 inches per mile, which is also Pavement ME's default value. And then you would reconstruct once that threshold value was reached. And then that process was repeated. The next scenario that we looked at was crack sealant, where you would go out, you would crack seal every 2 years until your IRI, your terminal IRI was reached, and then you would reconstruct. And through literature review, we found that by performing the crack sealant treatment, you're able to extend the service life of your roadway by approximately 2 years. The next alternative that we looked at was microsurfacing, and we had 2 different trigger or timing values on when to apply that treatment. So we looked at whether it was done at 140 inch per mile or 160 inch per mile threshold. We also looked at cold-in-place recycling and a 2-inch mill and overlay. And I'd like to just note that for the analysis period and how we determined when we would stop the maintenance cycles was that we wanted to have a minimum of 3 full cycles for each cross-section be performed. So we want to allow a substantial amount of time to be able to make a fair comparison among the different alternatives. So shifting gears here to some of the results, the first result I'd like to highlight here is when we go from using just assuming baseline condition to using realistic traffic data in our LCA, we saw that there was about a 6.4% increase in our global warming potential and our cumulative energy demand when we used realistic traffic data in our LCA. So there was an impact. And the takeaway from this isn't so much that value, but just the fact that we saw a difference. And so this was for a 16-mile stretch near Boston, Massachusetts. But if you take this framework and you apply it to a different road with a different set of traffic and congestion, that value may either go up or it may go down. Shown here, bear with me, there's a lot on this slide, and we won't stay here long, but this is really just to show the impact that future climate can have on the timing of your performance curves. And so really here we're highlighting whether you use historical climate data to do your planning or if you use future climate data to do your planning. Now, if I take this back to a bite-size kind of view, and we look at just the do nothing and reconstruct in red, and the mill and overlay in blue, time in for our maintenance curves, right away we can see that the terminal year for how long it took to do 3 full cycles of each one of those maintenance types has significantly decreased. So we went from the year 2154 to the year 2116. And we can also note, highlighted in the green circles, the timing of when I'm highlighting here the mill and overlay, the timing of when that treatment is applied, and the frequency has now changed as well. And so this is important for decision makers to have an understanding that by using future climate, you can have a better estimate of how long those treatment types or scenarios are going to last for planning of resources. So shown here is looking at, from an agency's perspective, the maintenance and rehabilitation cost comparison. So this is all in net present value with a discount rate of 4%. And the color coding scheme here, green is denoting our most economical option and red is our least economical option. The top table is the analysis performed using Pavement ME's just historical climate data to generate the curves, and then the bottom table is using future climate data. So you can see that in general, from the 2 different tables, the ranking of the different maintenance alternatives is consistent. So mill and overlay is our most economical choice, while the do nothing and reconstruct is our least economical. But what is different here, if you look a little bit closer, the average percent difference in terms of net present value, as you go from the left percentages to the right, when you use future climate data, that value has now increased. And that is all with respect to your most economical option, the mill and overlay. So to really kind of drive home that point, if we look at just that average percent increase in terms of net present value, when you use future climate data compared to historical climate data, you can see that those percentages are increasing. And I'll say this with a caveat or a warning that we might be able to draw the conclusion that for this highway and the assumptions made in this analysis, that the mill and overlay or the cold in place recycling could be a more resilient maintenance alternative compared to, say, microsurfacing, which increased by about 77% in terms of net present value when you use future climate data. So I'm going to show kind of a subsequent set of slides here with very similar plots, so just to get acquainted with some of our LCA results. I'm showing right now the global warming potential for one of our cross sections, and we're looking at 2 different mixtures with the 6 different maintenance types. The green is showing your user impact during the from your operations phase, and the orange is showing your construction or your maintenance. So looking at it from an agency's impact, and you can see that the total sum of those bars varies, but also the individual components of those bars vary. So if we try to optimize our global warming impact in terms of from a user's view, we can see that there's a 19.6% difference in operations impact from a user's perspective. Similarly, if we do the same type of analysis, you can see that there's a 70% difference in terms of an agency impact. So a very similar plot, but this time looking at the total energy consumption. And it's no surprise that they follow a very similar trend. But if you try to optimize from a user's perspective, you can see up to a 17% difference in impact, and you can see up to a 70% difference in agency impact. And then lastly, looking at the yearly cost comparison, once again, dependent upon which type of maintenance treatment you have, as well as which cross-section, it varies. And one takeaway too from these plots is the green portion of the bar, which is accounting for your user costs and impact, is significantly larger than your agency cost or impact. So it's really important to take a look at both and not just only focus on your agency costs when planning. Now, if we try to optimize from a user's perspective, you can see about 17.7% difference in yearly costs, and from a agency's perspective, you can see up to about a 41% difference in agency costs. So in conclusion, one of the first takeaways from this study that we learned was that including realistic traffic data does matter, does have an impact. And we saw with this given set of traffic and case study location, a 6.4% increase in global warming potential and cumulative energy demand. We also saw that by incorporating future climate data, it does have an impact on those IRI curves as well as the frequency of when those treatments are required or applied. And we can see up to an 8% increase in users and a 38% increase in agency impact in terms of GWP or CED when using future climate data rather than that historical climate data. And in general, we saw that the ranking of those maintenance alternatives were consistent. So the mill and overlay was consistently our most economical choice, while the do nothing reconstruct was our least economical choice. But what we did see was that when you look a little bit closer, the gap between which option is the best is increasing when using future climate data. And then lastly, when you try to optimize your pavement structure as well as which maintenance type and the timing, it will have a trade-off between user and agencies in terms of cost as well as environmental impacts. And so it's really important to step back and to look at both perspectives, especially where users are contributing a significant portion during the operations phase of an LCA. So some areas for future work and how this study could be expanded. The first one is really to look at different maintenance and rehabilitation strategies. So look at a chip seal, look at a slurry seal. Does that change anything? Also to look at a combination of those maintenance strategies. So perhaps you would go out, you would crack seal every 2 years, and then at year 10 you would do a microsurface. And does that have an impact? We could also look at the effect of future climate data on those maintenance and rehabilitation strategies in terms of IRI. As I mentioned, there's really limited literature out there on that, and we also don't know how that will perform under future climate conditions. So there's an area there to be explored. The same framework or LCA that was kind of presented today could also be done using a probabilistic approach rather than a deterministic approach in order to account for some of those variabilities in terms of input and uncertainty in, say, fuel price cost or discount rates, things like that. And then lastly, there should be really just a continuous effort to improve our operational impact component of our LCA and to get a better understanding on how we can do a good job of accounting for both users and agencies' impact, as well as incorporating that real-time traffic data and future climate data into your LCA. And for example, there's been a lot of recent work out of the University of Nevada, Reno, as well as the University of Nottingham. And with that, I'd like to thank Dr. Sayas and the UNH Center for Infrastructure and Resilience to Climate, as well as the UNH Materials Research Group and the International Society for Asphalt Pavement for the opportunity to present today to you all. Thank you.
Thank you. Now we're going to have our last but not least presentation. That's going to be done by Ron. Mr. Corun is the Specialty Product Sales and Marketing Manager for Associated Asphalt Partners, LLC, a major asphalt supplier founded in 1948 with headquarters in Roanoke. He graduated from the University of Maryland with a bachelor's in civil engineering. Previously, he worked for 20 years as the Director of Asphalt Technical Service for Axion Specialty Products, Manager of Asphalt Technical Service for New Star Asphalt LLC, and the Senior Technical Manager for the Citgo Asphalt Refining Company. Prior to those positions, he worked for 33 years for Corum and Getch, an asphalt paving construction firm founded by his grandfather. He has worked extensively in all areas of the asphalt paving industry: labor, equipment operator, plant operator, quality control, and mix design technician, super independent estimator, and general manager. He serves on numerous committees of the Asphalt Institute, the National Asphalt Pavement Association, the Association of Modified Asphalt Producers, and is currently co-chairman of the Northeast Asphalt User Producer Group. He is a member of the TRB, the Association of the Asphalt Pavement Technologists, and Who is Who in America. Please welcome Ron.
Thank you. Good afternoon. Appreciate the opportunity to make the presentation. The previous presentation by Katie was focused mostly on use phase of asphalt and looking at LCA, whereas this one on behalf of the Asphalt Institute is looking strictly at the LCA impact of the material itself. Of course, quick definition of LCA, probably don't need to throw that up there. Katie did a very good job talking about LCAs, but looking at the inputs and outputs and the potential environmental impacts of any particular product. And of course, we look at a life cycle data for asphalt, and why do we want to do that? And this was a decision we had to make as an Asphalt Institute, saying, you know, there's other studies out there, there's LCAs out there. Katie had to get information from asphalt from somewhere to use in hers. But why would the Institute want to do that? Well, first off, we wanted to make sure that we provided up-to-date and accurate information, and we had the ability to get actual information from our refining members that produce asphalt, where most of these other studies weren't able to do that. And we wanted to be able to support defensible competitive claims. It's certainly a heated environment out there, especially in the environmental arena between the concrete industry and the asphalt industry. The concrete industry spent a ton of money up at MIT to try to disparage our product, and we want to make sure that we had the most accurate information out there and something that we certainly could defend. Who's doing LCAs? And this slide was kind of put up there to help our members decide at the Asphalt Institute, do we want to spend the money and actually perform this LCA? And you look at the vast number of industries and companies that are doing it, it wasn't hard to make that decision. If you look specifically at the pavement level, you can see this list. Eurobatum has had an LCA and LCI, I think, for at least 15 years or so. And you can see NAPA has put together not only LCA, but an environmental product declaration program that its members can use for asphalt mixes. As far as our competitors go, both on the material side, the cement side, and on the concrete side, the ready-mix industry, all of them have LCAs and EPDs for their product. So what was our goal here? Again, we wanted to do something. Our membership of the Institute represents all of North America. We have a number of Canadian suppliers as well as those in the United States. So we wanted something that represented all of North America. We wanted to use actual refinery data. Again, most of the other studies we don't believe had that information available to them. And this would definitely be able to be used as an input into the EPD that organizations such as NAPA had. The biggest thing is we wanted to develop a methodology looking at the refinery process to be able to allocate or subdivide all the impacts that go on with all the products in a refinery. If you looked at previous studies, most of them looked at a refinery as a big black box and say, okay, here's the inputs, here's the emissions. If asphalt is 10% of the stream coming in out of that refinery, we assign 10% of all of that to asphalt. And that's really not fair, because if you look at all the processes in a refinery, there are a lot of processes. Some of them are very energy intensive that have nothing to do with asphalt. And the biggest thing of all is if you look at the asphalt, it's the only product coming through the tower that isn't vaporized and then recondensed. So we're looking at a product that is different than all the other refinery products, and that hasn't been addressed. We wanted to have agreement on our side with American Petroleum Institute. If you look at refineries and all the products coming out, asphalt's certainly not the predominant product. And at some point in time, API is going to have to do an LCA on all of the other products in their refinery. And if the methodology for the majority of that products in that refinery stream don't agree with the one that the asphalt industry had, then again, that makes us really open for attack by our competition. And we knew that Eurobatum had a methodology that they used, and the European equivalent of the Asphalt Petroleum Institute, Konkawa, did not agree with Eurobatum's approach. So we were trying to get an approach that not only here in the United States had agreement with API, but also had agreement across the water with both Eurobatum and with Konkawa. So if we look at the outputs of the LCA, of course, we're looking at life cycle inventory, we're looking at emissions, we're looking at resource consumption and waste. When we look at the categories here, primary energy demand, and of course the impact assessments. As Katie mentioned, one of the major ones, global warming potential. There's a GWP 100 for the 100-year global warming potential. There's a GWP 20 for a 20-year global warming potential, acidification potential, eutrophication potential, smog formation potential. So all of these things are reported out of an LCA. If you look at our product, we said, okay, what are we going to study? What's this study going to cover? Well, first, we're looking at a typical neat asphalt binder coming out of a refinery without any additives of any kind. We also wanted to address not only refineries, but terminals. A lot of the asphalt here in North America is sold through terminals, not necessarily directly from a refinery, and there are certain things that are put in at terminals. So we wanted to look at an asphalt that was modified with a styrene-butadiene-styrene polymer. We looked at one that was the terminal blend process, one that had ground tire rubber added to it, and also one that was modified with polyphosphoric acid. We felt these additives were things that were typically done at a terminal or at the refinery, not done in a hot mix asphalt plant. If you look at where we are across the timeline, across the bottom here, starting from when we had our kickoff meeting, data collection, we're right now in the final phase. We have gotten an interim report, final report, and we're having that addressed by a critical review panel, and we're addressing those comments at this point. So again, declared unit at the top there, we're looking at 1 kilogram of asphalt binder, and we looked at average numbers for the additives. Now again, 1 kilogram asphalt binder, 3.5% SBS, 0.5% of polyphosphoric acid, 8% ground tire rubber. However, the end user can modify. If they're using a different amount of any of these additives, they can modify the results to reflect their actual usage. These are the participating companies, again, both in the United States and from Canada. You can see our refinery members and our terminal members. We wanted to cover both, again, because a lot of asphalt is sold through terminals. There's a map giving you a representation of North America. We had a relatively good distribution. In terms of facilities, we had 12 refineries from 9 different companies. That represents about 35–40% of the total number of asphalt refineries in North America. And we had 10 terminals from 4 different companies. Okay, if we look at this allocation now, looking at the refinery and all the co-products that come out of the refinery stream, you know, how do you account for that? How do you allocate to asphalt its true fair burden? Under ISO, and this is an ISO process, there's a number of ways to do this. The primary one and the most favored one is subdivision. Divide the process into 2 or more separate inventories. System expansion by substitution. This one doesn't work at all here. We can't substitute something else for asphalt, so that one doesn't work. If you look at allocation, that was a methodology, and it's third in line, so it's the least favored methodology by ISO, but that is the one that's been used in all of the previous studies for asphalt LCAs. So you can consider when you're doing allocation, you can look at by mass, by economic value, or by any combination of those. So, as I said, mostly in the past. It was all based on allocation method. If you look at our study, we did electricity by allocation based on mass, crude oil by energy content allocation, thermal energy, and this is where we've differed from everyone else. We did a subdivision rather than allocation based on simple thermodynamics. Every other product coming through that refinery stream, as I said, is vaporized. Asphalt is not. The only energy going into asphalt is the energy required to raise the temperature of that crude oil from the temperature in the storage tank of crude oil to the rundown temperature, the exit temperature of the asphalt actually coming out of the refinery unit. All that uses is sensible heat. No latent heat involved, which is a factor that's required in every other single refinery product. So we base this on simply thermodynamics, on how much energy does it take to raise the temperature from the crude oil temperature up to the asphalt temperature. Direct emissions, again, this was allocated on energy use. So if you look at a comparison here of former studies, Eurobatum used crude oil by mass. They used an economic analysis on electricity and thermal energy, again, economic, but it was all done on allocation method. The GABI database that you see up there, that is a database, international database that has been put together by the consultant company we used on this project, ThinkStep. And in the past, all of their methods, their allocations were done, again, using the allocation method using mass. So this is the big difference in ours, the fact that we're now using a subdivision. Okay, I'm not going to go into calculations. Sensible heat, latent heat. We looked to validate. ThinkStep said we really can't put this forward unless we can validate this. Every refinery has an extremely complicated and proprietary model that they use to simulate the processes going on in those towers. And they can calculate all the inputs, output, energy required, all of those things. So we wanted to try to validate this very simple approach to somebody that was using that process simulation software. One of our companies volunteered to do that, not only at one refinery, but two. So basically, they ran their process simulation model and said, okay, here's the inputs and outputs if we run 10,000 barrels of asphalt, and here's the same study if we don't run any asphalt at all. What's the difference? And when we compared that to the simple thermodynamic approach for production of 10,000 barrels of asphalt, we were then 1% of the process simulation software. So based on that, ThinkStep said that's certainly accurate enough. We move forward with this approach. Well, what were the results? Number of surprising things out there as far as we're concerned. If you look at which parts of the equation, and again, our basic boundaries on our study start at the wellhead, from getting the crude oil out of the ground to the terminal gate or refinery gate, wherever the contractor is picking up that asphalt. And if you look at what provides the largest component, that big blue circle there is crude oil. The impact of extracting the crude oil and transporting it to the refinery, especially in the extraction process, is by far the largest component. And what drives that is depending on what type of crude oil you're looking at. If you look at the bottom there, the red part of the circle, the crude from oil sands, 54% of the participants in this study said they were running crude oil sands as their primary crude source for making asphalt. And if you don't know, the energy required to extract that material from the ground and to wash the oil out of the sand and go through all of that, it is by far the most energy intensive crude oil that you can possibly use. If you move over to the next step, the tertiary extraction, now we're talking about crude oil that's so heavy it requires some assistance, whether it's steam extraction or whatever, steam injection, to get that out of the ground. So if you look at most of the crudes that were in this study, unfortunately, it was the ones that take the most energy to get, and that was the biggest factor in our final number. So you can see of the crudes used in this study, and now we ask our members, give us the crude slate you use when you're making asphalt, because refineries run in different modes. Sometimes they do not make asphalt, and of course they may actually be running a different crude slate at that time. So if you look, you can see again, the biggest part was the oil sands, tertiary and secondary, and then the smallest, primary extraction. So that was they're the ones easiest to get out of the ground. So you look at global warming potential and say, okay, what drives our number, or what drives our number mostly? It's the crude oil. So if you look on the chart and say, okay, global warming potential, here's where our crude slate is, based strictly on the crudes. Compared to Eurobitume, well, Eurobitume is not running any type of crude that requires tertiary extraction or any oil sands. So that made the big difference between ours and theirs. And again, you can see crudes that require primary extraction much less. When you get up to the oil sands, you can see why that's driving our number where it is. So where does that put us for the numbers for global warming potential for the 4 different asphalts we considered? So if we look at just the plain asphalt global warming potential, 0.68 kilograms of CO2. If you look at asphalt with ground tire rubber, since we've got a recycled product, we're getting credit, so it actually lowers the number by about almost 3%, down to 0.66. If we look at PPA, that increases the number by 2.9% up to 0.70. And we look at SBS, that one bumps us up by 19%. And that's strictly due to all of the impact of producing the SBS polymer that we're using. We look at the relative contributions to the numbers that we ended up with. And again, all the numbers, global warming potential, energy demand, acidification, eutrophication, smog formation. You can see crude oil is the largest one in all of those by far, especially in energy demand. You can see, especially looking because of the amount of oil sands, energy demand just dominates on that level. The other thing to look at also is that terminal is not insignificant. It can be a substantial number. And what you need to know is that the Eurobitume study included no terminals, and perhaps everything sold directly out of a refinery in Europe. I don't have the knowledge of that, but they did not include any terminals. And previous studies done, I think the one that was used by Napa did not include terminals either. So that's something that really needed to be included. If you look at impact on terminal operations themselves, and where is the biggest contributor, you can see we're looking at the SBS is a substantial number added to the terminal process. Most of the terminal numbers are based on thermal energy, the energy required to keep the asphalt hot in the tanks, very simply. If we look at relative results for terminal operations, again, thermal energy, certainly the biggest one. Transportation can be a big number, especially for some of these items. So thermal energy and transport add up to quite a bit influence into the terminal operations. So we do a benchmark to previous LCAs or LCIs. You can see where we stand, the Asphalt Institute number, Eurobitume. This is U.S. bitumen. This is under the GABI database, again, using the average U.S. crude slate, which does not reflect the crude slate our members are running, and the Napa tool is in here. So, okay, the number's higher, and mainly because of the crudes. That was a concern for us. It's a concern for Napa when we started leaking out information. We don't have a final report at this point, but we certainly know our numbers are going to be higher than what they used in the past. That's not where we want to be, certainly. But we do know that, again, the reasons for it, mostly due to crude slate, and mostly the fact that terminals were not included in anybody's study previously. But I can tell you that Eurobitume has been in the process in the past 6 months of revising and redoing their LCI, and they are now using the subdivision method, the thermal energy method that we're using. They have gotten a buy-in from Konkawa on that. So we got a buy-in from API. So now one of our goals has been reached. We have a complete agreement between ourselves, API, Konkawa, and Eurabatum on using the approach in the refinery for determining the LCA for asphalt. And again, the GABI tool previously and the NAPA tool, again, used an average crude slate and didn't include terminals, which is the biggest difference. ISO does not require a critical review panel. We decided to go that route. We have a panel of 3 experts in the industry. We sent out the initial report to them, and they had hundreds of questions and comments. And the contractor, ThinkStep, has been addressing them, is almost finished. But some of the early comments caused ThinkStep to go back in and relook at some things. And we immediately have some reductions based on some of the errors that the critical review panel caught, or differences of opinion. Some of them are relatively minor, 6 and 8%, 17. But here, ozone, 82% drop. That's pretty substantial. So we're again looking forward to the final report here, probably within the next 30 days or so when we finish up. Again, looking at other numbers, we're still looking at total reductions, and we could actually see lower numbers yet when we get the final report. First time I put this slide up, I got chewed out by some folks saying you can't do that. You know, you can't compare asphalt to concrete. Anytime you're looking at these kind of numbers, you have to look at, you know, the product category rule, the boundaries that people pick. If they're not identical, then these numbers mean nothing. But we wanted to benchmark ourselves and say, okay, let's assume that we're pretty close between what we're doing and what the concrete industry is doing in terms of the boundaries. And let's just see where we stand. We know our numbers are higher than numbers used in the past. Does that really hurt us that much? So if you look at the numbers and you look at our numbers, this is a mix that contains 20% wrap, 5% asphalt binder. And the numbers for the concrete came directly from the National Ready Mix Concrete, EPD. So we feel pretty good about that. And you can see that our numbers here at 0.68, and they're up probably double us, at least double us. Now people say, shouldn't do that, not allowed. ISO says you can't do that. Industry experts say that. But states and agencies are starting to use this stuff, and they already use LCCA to compare the two products. And I can promise you that someone somewhere is going to try to do the same thing here. So even though this isn't kosher, I did it anyway to give us a benchmark. The other thing is, you look at these numbers and say, based strictly on the material, there's no way, because we know that cement is the second largest contributor of CO2 in the world, only second to power plants, that on the material side that they can compete with us. That's why they're putting their money into the use phase. That's where Katie's talking about. You saw the bars on her chart. The blue bars for use phase and the yellow bars for the actual construction and the material, the use phase dominates. So that's why they're trying to tell us that, you know, asphalt increases the resistance to rolling, and that the vehicle interaction, that concrete saves emissions and saves fuel, and that's why they're focused, because there's no way they can win this side of the battle. Okay, conclusions. So we went cradle to gate, starting at the wellhead. So we're looking at 0.68. It varies from 0.66 up to 0.81 depending on the additive we're putting in. It's mostly dominated by the crude slate. And that crude slate was specific to our refineries. And of course, ours did include terminals, which hasn't been done before. And it says February, we're already past that. We're still, our contractor's still addressing some critical review panel comments. So we'll move that back till April. But anyway, at this point, we're looking to have it completed soon. So with that, thank you.
Thank you very much, Ron. I'll ask the other presenters to come here again. And we are going to start and also Professor Eshanda, Dave. I guess I'll put some chairs here. Last minute arrangements. Okay, I guess now we can start. We have all the presenters and also Professor Eshan Dave. He is the advisor of Katie, along with Professor Josias. I will ask you to stand here if you have any question. The question can be directly to one of the presenters or it can be a general question. I'll just ask you to give your name and your affiliation, please.
Hi, Gerald Ranke, Matthew Construction. Heather, I may not have been paying close enough attention, but you talked about resiliency, and that struck a chord with me. But what types of materials, what types of outcomes would you have to have before one can say, okay, I put something in an asphalt, and it gave me more resiliency?
No, that's fine.
From an environmental standpoint.
You know, I think that's going to probably depend from state to state and agencies. We're really early on in this process and really discussing some of those topics right now on what it means specifically to pavements. What I wish we were further along. We started this project probably about a year ago, but I highlighted most of the stuff that was related to the planning side of things, and we're really now diving into the pavements right now and trying to come up with some guidance such as that. So I know I didn't really answer your question, and I'm having a very hard time seeing you.
That's okay, I'm not worth looking at, so.
No, that is much better. Oh, I mean, it's blinding when you can't even see anything. But I don't know, did you have any follow-up question? Or?
Yes, I mean, would a resilient pavement be one that lasts 50% longer, 20% longer? Is that kind of what the concept is?
It could be, or it could be the pavement that lasts what we expected it to. I mean, I think when we design something, we have a prospective design service life. We may be reaching those conditions much earlier, right? Remember there was a presenter a while back at one of the sustainability conferences that Napa hosted that would say, how often do we go out and see if a pavement that failed actually met its design life, it met the traffic increased a lot faster, the environmental conditions changed, and we don't often do that. So I think it doesn't necessarily mean it has to last longer. And certainly it will be different depending on what that road is providing. I think in Delaware, for example, they have a roadway that is going to a small community, and they're looking at, it's right now experiencing flooding every day, and it wasn't in the past. And there's another detour. It's not as long as what Australia has. It's only 2 minutes. And so they're looking at abandoning this roadway. So I think it's going to change how we look at different problems, and it's going to be area specific on the design life.
Okay, thank you. Katie, good to see you again. You were talking about the costs of materials, mill and overlay versus microsurfacing. It seems strange to me that a microsurfacing would be more costly. What factored into that? Is it the fact that you had IRIs that were higher than 100 were your default starting points, or why do you think it was more expensive?
Sure, great question, and good to see you again too, Jerry.
part of that is a function of the discount rate. So when you're bringing it back to net present value, depending upon when you're generating those performance curves, the timing, and what year it's being performed, and the frequency of when that maintenance treatment is being applied. So when you rerun with a mill and overlay or the microsurface, your IRI, it's only resetting so far, and so your pavement is still going to deteriorate much faster than if you had, say, like reconstructed and you have a brand new structure. So it's a function of the number of times that treatment is applied when you're comparing it, as well as part of that discount rate.
So if I want to paraphrase that and see if I got it.
Sure.
The microsurfacing doesn't give you the same pavement surface quality that you would get from basically a reconstructed or a mill and overlay pavement.
Sure, correct, yep.
Okay. Thanks.
Yep.
Mike Heitzman with the National Center for Asphalt Technology. Katie, I'm going to also ask you a question about your study. And you ended up with a 100-year
analysis period.
Future climate.
Yep.
And you mentioned one model, but there's a lot of different models out there that actually do future climate. So how did you choose the one that you used?
Good question. So yes, we used the CMIP-5 data to do it, but you are correct in that there are many models out there to use. We had chosen this one, because we were able to get precipitation and temperature data for our case study location. So that was certainly of interest for us, as well as the method in terms of incorporating the daily data into Pavement ME was kind of readily available for us to use to do this analysis. So that's really why we use that for this study. But you could do, again, like you said, with another database that might have a different coverage range, could be done as well.
So in my follow-up then, how did you go from daily climate to hourly, and did you use a climate scientologist to do that?
So we used a method that was proposed or developed by Valet et al. in 2017, where really it converted the max and min daily temperature. So if we're just looking at the temperature part of it first, and it used where you break it down into two portions of your day, where you have your peak, and then you have a second peak in terms of warming and cooling in the day and at night. And then I know perhaps, Dr. Darway, if you want to explain a little bit further that part, but for the precipitation, it was taking a total precipitation value for a day, which we were able to get from the CMIP-5, and then just split that into 24-hour equal increments and input that into Pavement ME.
Yeah, on the temperature side, was based on a previous meteorological work where they have been able to come up with a mathematical function that has shown 90% confidence interval, where if you know your maximum and minimum, you are able to get to your hourly rate. And as Katie mentioned, on precipitation side, we are not that concerned, because when Pavement ME is run, it's not really as sensitive to moisture changes on hourly basis. It's really doing more on monthly or seasonal basis. So, yeah.
Very good, thank you.
Thank you.
Irv Ducatz, Matthew Construction, mainly. Flyer ELD Consulting, sometimes. First, another question for Katie, and good seeing you again. Excellent presentation. And in your increase in general cost using the real numbers, the question I have for you is the effective initial IRI a linear function, or is it an exponential function? And I'm going to give you some background on why I'm asking this particular question. Is some agencies are very proud of their pavement programs and provide incentives for getting smoother roads. And so my question is, if a state average is, say, 20 inches per mile lower than what you've shown, what you used as an average, would that help offset that increased cost of using real data?
That's an excellent point, or excellent question. I think the first part to address that was we had selected 63 inches per mile was that initial IRI value, and that was really just in terms of a default value from pavement ME to start with. But again, the methodology and what was presented today and those cost values is really just showing a framework that could be used. So if you were to take a step back and use more of like a probabilistic approach where you could look at, does the effect of that initial RI value matter, and how significant does that have an impact on your results, is certainly another step in the process that could be looked at in continuing the study or a similar study.
And then for the whole group, so we're not asking all the questions of Katie, I've heard a couple times in different presentations of using real data or sensible data. Do you see this as a shift and a necessary shift that needs to be in all the life cycle cost analysis, is to, instead of going on historical data, is to actually use present and future data?
I do. I think if you look at the age of IT and information in trends, a lot of other industries have used big data. It's been slow to come to the construction industry, I think, especially with the emergence of building information models that will facilitate this blockchain and information flowing from one to the other. I don't foresee this moving away from this direction. I foresee us going forward down the path and using not only the best data, but using the data and learning from it and making better decisions moving forward. Want to say anything? Okay, next.
Yep. Okay, I'm Jeff Rowe with AAPT. I enjoyed this presentation. I've got a couple of questions, but I'd like to start by asking about strategies for dealing with coastal inundations, with floodings and these types of aspects. We were involved with some of the Sandy work and then also with the 2016 flooding that they had in Louisiana. And in particularly, I'm aware that New Hampshire has done some work looking at a framework for evaluating pavements, but I'd be interested in what the panel's view is on this aspect and whether other countries are also developing frameworks for looking at pavement performance.
Sorry, so your question is, are we using adaptive frameworks? And are we creating our own?
Correct, yeah.
Yeah.
What's the plans that you have for looking at pavement performance when you get a coastal inundation or flooding or other aspects of major flooding? It might not be coastal, could be other regions. But you know, is there a framework, say, for example, you're developing in Australia? I'm aware of the New Hampshire work, but what other work is being done by federal or state organizations to develop those frameworks?
Yeah, I'm not sure in Australia personally. I will take that question back. I'm not sure if Eric knows of any in Australia that we're doing. But yeah, it's definitely something, I mean, I can't see it not being something that we're probably looking at doing. At the moment, we are just looking at adapting from, as I said, like the PARCs, or the international, the World Association frameworks that are out there. Does anybody else know?
From FHWA, the guidebook that I spoke about, it will have several methodologies, probably clustered by environmental conditions that you may expect. One of the methodologies, I mean, it was quite complex, Katie's study, to show how you would put the futuristic climate data into pavement ME. That would be one, but the other would be what would you do for flooded pavements specifically? I know we also have collaborative agreements with other countries, and this is a high importance to the Netherlands, and they've done a lot of research and work. I know that the Netherlands, they have not only pumping systems as well, but they're looking at the open graded friction course, and they're looking at creating lift thicknesses that are much larger to be able to deal with some of the capacity of the stormwater runoff. So that's one potential that we could pursue further at FHWA. There's some discussions on the next round of collaboration with the Netherlands. And then another area is fires. That's been the recent, and this wasn't your topic, but that would be another topic of interest, is there any damage to pavements because of fires? You know, what is it? What do you need to know? And from the studies that I've seen right now, you really want to know assess the damage, or not assess the damage, you really want to know the network performance before an event happens. And that's really important for the funding side, because in emergency relief funds, we provide funds to agencies to get it up to the state of repair of where it was previously. And so if an agency doesn't have good record keeping before, and this goes to, again, the big data question, it can really hamper the funds they would receive to improve their network after a major event.
Jeff, thank you for this question. It's really an excellent question. And as you mentioned, there's just two different studies I'd mentioned. One was actually a FHWA study that just recently finished. Joe Sass was the principal investigator on it. That one was focused more on short term, where it was looking at after flooding what kind of tools you can use to make decision as to when it's the right time to open to traffic. And that's really important from things like emergency responders perspective, or be able to at least provide, get your emergency supplies and so on. On the long-term side of things, we have currently a PhD student finishing up her thesis where she presented this work at TRB, but it really focuses on more of what kind of framework an agency would need, with all the details in terms of changes to their design processes and their maintenance processes, and really came up with a hybrid approach that's combination of top-down and bottom-up. And what that means is what kind of input changes you would need, as well as what kind of system changes you would need to look at next 30, 40, 50 years, especially in coastal areas, whether you are just raising the cross sections, whether you are placing what you are doing with your materials, what you are doing at the time of reconstruction, as well as at the time of rehabilitation. So again, as an example, not necessarily of pavements, but especially in New England, all the recent expansion that has happened at Boston Logan Airport, they did a vulnerability assessment, and you'd see that all new construction, they actually ended up moving all their equipment to second floor, and that's really in anticipation of flooding. So all the critical equipment at Boston Logan is for the terminals is now no longer on the first floor, but moved to second floor. So I think we need to do something like that on the pavement side as well.
Thanks. I think it's an incredibly important area when you consider the amount of our world population living in coastal regions. I have a second question, which is probably more aimed at Ron, but I was very interested in your information on the differences in the carbon output from the US to the European, and I wasn't really aware of that, hadn't quite thought of that in the same way. But I'd be interested in your comments on the expansion which is anticipated in the pipelines from the Western Canadian region, and as to how that might impact that number in the long term, and also whether there are any other global impacts in terms of the way that we're refining and producing bitumen that might change the balances in terms of how you're using fuel to refine bitumen.
There are so many factors involved in refining operations, and I mean, you could throw into that mix IMO 2020. How will that affect crude slates? That may affect crude slates more than any other factor, and it would be hard for me to say there's any one thing. I mean, basically, you know, the European market are using crudes that are certainly much more less energy intensive to get out of the ground than the ones we're using. And plus the fact, like I said, they had no terminal included in there. So completely different numbers. I mean, that works for them. What we did, have confidence in works for us. And we understand that, you know, the fluctuating crude situation changes all the time, whether it be pipelines or IMO, whatever. So we know we're going to have to go back in a couple of years and probably go through this again. And at this point, the methodology set for us. What we really need to do at that point is get an idea of crude slates from our members. And that's something we'll continue to have to update. That's all we can do.
Thanks, Ron.
John D'Angelo, consultant. Really interesting discussion this afternoon. My real question, though, is that it seems like this is a very large integrated process. And we had presentations on different aspects. I think, but the most broad one I saw was from Australia, where Melissa talked about you got the geometry that you're adjusting. You're actually adjusting your structural design and the materials, and I was just wondering, from some of the others, how you thought about sort of integrating it, because if we take this as individual small aspects, whether it's the asphalt and whether we do an overlay or a chip seal or something, they're only small little things where it's going to be this major large picture that all has to be integrated. So I was wondering if some of the other groups might have looked at some of that.
We are working on our project for the guidebook on the resiliency for pavements with the planners and the environmental group. It's going to be a joint project. But I do think and agree with you 100%, integration is key. And I think sometimes, at least what I've noticed, is you'll have the high up planning level approach working on something, and deep down in the weeds, the pavement engineers working on something, and we come up and a conflict emerges where the two don't quite intersect. But recognizing that we are trying to work more collaboratively within FHWA to address a more integrated design approach.
I completely agree with the point, John. I don't think just looking at smaller pieces of puzzle would cut it in grand scheme of things, but what these presentations, or many of these presentations, are showing is the tools that we need at those level, and then eventually all of those will have to come together. I mean, one could make some geometric change, and that could offset, I don't know, all the impact that might be coming from just changing materials. So completely agree, but we have to get there, and I think we're at the stage of walking before we get to the running stage.
Oh, no, I think this is all excellent work. It needs to be done. I just wondered, have you seen any effort at integration, again, for the implementation type of thing? That's all I'm asking. If you've seen that.
I can just say from my perspective, I think what Heather mentioned is probably that guidebook is going to be as advanced of information source as there's ever going to be. At least right now, I don't think there's anything else out there.
Okay, Randy West, National Center for Asphalt Technology. The question's probably for Katie and Ishan, but anybody that really has input on this question. It's about the use phase when you're starting to do an LCA. Do the models that we're looking at now, your model specifically, Ishan and Katie, and then others that may be out there, are they looking at the use phase in terms of fuel efficiency or energy efficiency of vehicles based on today's technology, today's mix of vehicles, or are they considering future improvements in energy efficiency of the vehicle stream into the future?
So I'll give a stab at it first, I guess, here, but it is based on today's vehicles, I guess, ability and its specific power, things like that. I know personally I've also done a little bit of work where we looked at doing a sensitivity analysis to the vehicle's energy demand. So if you imagine that with time, vehicles are going to get more efficient. Right. So looking at, kind of each decade, if we can improve the efficiency of our vehicles, as well as looking at the change kind of in fuel price and cost and things like that. But consistency with that, you are still seeing that increase with the use of that realistic traffic data component in the use phase. But we have done some preliminary work to look at that if you don't assume that your vehicles are kind of stagnant, but that they are improving in their energy demand and consumption and things like that, how that plays out.
Okay, so your model that you used did not take that into account, but it can be looked at in other models or in future analyses of your procedure.
Exactly, yeah. You can do it either, like a Monte Carlo simulation, you can do a sensitivity analysis, however you want to look at it, but there are ways to try to incorporate that in, but what was presented today did not include that, correct?
I just think that, with the advancements that we are seeing in technology, whether it's, electric vehicles, more fuel-efficient tires, tire designs, more aerodynamic designs for vehicles, platooning of trucks, all those kind of things. If we try to use today's mix of energy efficiency of vehicles, and project that into the future, 50 years, 100 years, we're going to be way off the mark.
Yeah, absolutely. I mean, we're taking those baby steps, but it's the same thing whether you're talking about, vehicle efficiency or, even climate data. We saw, like, when you're trying to make predictions in the future and you're using past data, you're really limiting yourself in what you can imagine, what you can estimate are really going to be the impacts in the future.
Thank you.
Only thing I'll add to that is that the results that Katie showed today did not include that, but she has, as part of her study, actually done that, where she looked at continually improving efficiencies of vehicles and looked at that as a sensitivity analysis. Yeah.
Gail Page, consultant. My enthusiasm for questions kind of wanes after 4 or 5 presentations. I always like to question after each presentation. But that being said, I'd like to comment on one of the presentations that kind of really hit home. I remember, I think it was 15 years ago at ASTM, I heard the word EPD and LCA and wondered, what the heck is that? But I soon found out is that if you're going to continue to market in the construction materials industry, you better be thinking about this and really having a realistic EPD and LCA for asphalt. Really, again, a comment on the Asphalt Institute is having the courage to put together realistic numbers, even though they are double what they were previously, I think is the right way to go, and having the right methodology to update that EPD and LCA is really a tremendous effort that should be applauded, because it's going to continue to make our product viable with other products. There are agencies out there, and I think the one in California was 15 years ago that put that out there for bid for construction materials, concrete versus asphalt, and having an LCA and EPD, which there was none for asphalt at the time. So thank you for the Asphalt Institute for doing that.
Jim Malthrop, FP2. Following up on Gail's comment or question, what are the regulatory implications of what you've discussed?
With regards to EPDs and LCAs?
Yes.
FHWA right now doesn't have anything with regards to LCA or EPDs. Currently, we are gathering information regarding our pavement design policy. And pavement design policy right now just specifically looks at traffic impacts, your environmental conditions. You must consider those into a pavement design and then look at the best performance and cost effective. Now, from the listening session, it was mentioned, LCA, sustainability, resiliency, those were all some words, mentioned, but we're just gathering information with the states. As well, and so we'll do peer exchanges as well moving forward. But that doesn't mean that there's regulatory changes. It could be research that we pursue. It could be technical guidance, program stuff, or it could be regulatory. We're looking at it from a whole big picture, pavement design policy. Now, on another side, at the state level, California was mentioned. California does have legislation that does require the use of, or asking for EPDs right now, and so they're doing some pilot studies and encouraging the industry. There's exclusion of both asphalt and concrete providing these EPDs as of now, but they are including them in the pilot studies, and I think, I can't speak on their behalf, but it seems like they may be going forward. And then Oregon also has some activity where they're looking at it. They're morely being sponsored by the Department of Environmental Quality. So the Department of Environmental Quality in Oregon looks at helping communities improve their environmental footprint. So they do benchmarking and hotspot analysis, and where they can determine what purchasing decisions will have the biggest influence, and pavement materials is one of them that always comes up. I think the industry has been fortunate and dodged a bullet for many years because nobody really wanted to tackle that decision-making process, but now it's coming. And so I know that they're looking at it, as well as Washington State has a pilot project on how EPDs would be introduced, and Minnesota DOT has a pilot project. They're reaching out to stakeholders. I have a meeting with Minnesota this month, in a couple weeks, on their EPD. And then Arizona is looking at doing another pilot study as well. So those are the states I know that are looking at EPDs. It will most likely come from a state and local level, to answer your question.
Am I understanding correctly that in California in 2021, it will be a requirement in order to do work there?
I don't have the cheat sheet in front of me that Jackie sent to me, but I could give you those dates. I do have that information, but it will be required from my understanding in the future, but I don't know the dates off the top of my head.
Well, as we know in the U.S., if it starts in California, it kind of has a way of spreading around. So,
yeah.
Thank you.
Do you have any other question? We still have 20 minutes. JP.
So I have a question for Ron. And Ron. No, I think this study that the Asphalt Institute has done is very good and very important for the whole industry. I'm just a little bit, I wouldn't say disappointed, but I think it's too limiting looking only at the cradle to gate. Whereas the product, as you mentioned several times, asphalt is not vaporized. It's one of the very few products from a refinery which is not burnt, actually, and which is made to last long. And it does. And it does a very good job making long-lasting pavements. And I think that in this competitive world, when we make that comparison, or even if it's not allowed, with the concrete, there may be some things to show there. And I think the other problem is, so you showed some data, and particularly, for example, that when you add additives or like SBS, of course, it increases the figures. But on the other hand, it increases the lifetime. So not looking at this part is sort of a little bit misleading, in my opinion.
I agree, but the idea here is that our numbers plug into NAPA's EPD. They cover it from the time the contractor picks it up and makes his mix. So you've got all those other factors involved with the aggregates in the mix. Of course, they need numbers from the aggregate industry. And then whether the mix plant's using recycled asphalt or whatever they're putting in, shingles or whatever. So, once it leaves our tank, we kind of have no control over whatever's in it. At that point, the NAPA EPD provides all the information for that. Now, so theirs is going to take it up through construction, and I don't know what happens in the use phase.
Would it be like a global
Yeah, we're plugging our information into the big picture.
And then, from an agency's perspective, it would be using an LCA, very similar to how we do life cycle costs. We would do a full life cycle assessment. So it would get there. It's just taking building blocks, and instead of using estimated data, you have better refined data.
Andrew.
Hi, Andrew Bram, University of Arkansas. And I apologize, Katie, I was not here from your presentation, but thanks to Dave's hard work, I was able to actually go onto YouTube and kind of skip ahead a little bit. So if you answered this already, I apologize. but I noticed how you used AAPT pavement ME design plus some literature in order to gather information about IRI decreasing after using maintenance treatments. And I was wondering, does AAPT automatically predict pavement deterioration when using crack sealant microsurfacing and cold in place recycling?
No, so that's where that literature piece kicked in. So cold in place and the mill and overlay in your baseline conditions we were able to do, but for that crack sealing and the microsurfacing, that was done through literature. So the crack sealing, as I mentioned in the presentation, found that you could extend your service life or your performance curve by 2 years approximately by performing that crack sealant every 2 years until the terminal IRI was reached. And then for the microsurfacing, when you apply that treatment, it's able to improve your IRI or reset it by approximately 45 inches per mile is what we had used and found through literature as an average value to use when you apply that treatment.
Okay, thank you.
Welcome.
Do we have any other question? So now it's my turn, I do. Well, can be to any of the presenters, but I guess mostly to the presenters that talked about the LCA. You have mentioned about the real traffic data. By the real traffic data, is the real axle configurations and number of passes and also the weight of the vehicles or not?
Yes, so the realistic traffic data that we took was from Mass DOT's data management system. So from there, we were able to get vehicle counts as well as break down vehicle classifications. So to look at the axle configuration, weight, and things like that. And so all of that was taken into consideration when we were looking at our emissions output for the MOVE software. And so we had to come up with the vehicle-specific power using guidelines and recommendations from NCHRP-720 on vehicle characteristics. So we were able to take data from that section or that highway and actually try to convert that into emissions data and impacts.
Very good. Any other question? Everybody ready for the reception? I think so. With that, I want to thank all the presenters. Thank you all for being here this afternoon, and I hope to see you all in the reception.